We're here to talk about building tips and tricks for making strong robots and effective attachments. So, as Maria already introduced us, my name is Eden, and I've been involved in FLL Challenge since 2007.
My name is Logan, and I was involved in FLL Challenge since 2010.
And if you knew us back then, this is us when we were on our team. So very small versions of ourselves. So we were on the W.A.F.F.L.E.S. Both of us started when we were 8 years old and continued for 5 years. And the W.A.F.F.L.E.S, as Maria said, we are a competitive team. We usually qualified for provincials, and when I was on the team, we qualified for the World Championships twice, or the World Festival, as a core values team. We've won several awards for robot design, robot performance, champions awards, all that kind of stuff. And we just want to share some of the things that we learned from our experiences to see if that will help you guys. We stayed involved with the program as referees, and we both mentored after we graduated, and now we're both involved in FRC. Logan's in his last year as a student there, and I'm a mentor. So the topics that we're going to be going over today are strong building, simplicity in design, modularity, and prototyping and iteration. And we'll have lots of examples, specific examples from things that we did, and just to show how it applies specifically within First LEGO League Challenge. And we'll have the questions at the end of the session.
All right. So I'm going to start us off with strong building here. So why is strong building important? It's really important because it minimizes how many times your robot is going to break and how many times it's going to cause your robot to fail on the field. It also increases your robot effectiveness in a similar way. Make sure that your robot is going to be as accurate as possible. Not going to have anything flailing around that could or could not work, unless it's intentionally flailing around. There's a few different ways you can kind of make this happen. The first one here, you can use the right piece for the right job. You don't want to be using a 2-beam when you can be using a 15-beam. You don't want to be using essentially really short things when you can be using long things. Just make sure you're doing the right thing. Make sure you're doing what the piece is intended for. Number 2, you can add cross bracing. So this is really helpful to strengthen your robot or your attachments. Make sure they're not going to be making giant parallelograms and kind of flailing all over the place. Number 3 there is avoid cantilevers. This is just something that's sticking outside of your robot for some amount of distance. We often use these on our wheels, as you'll see later. Helps you makes you more accurate. And the 4th one here is distribute weight. So this is just making sure that you're not having lopsided robots with all your weight on one side, causing your robot to constantly turn slightly in a direction, or dragging something on the mat. It's also going to do similar things, making you less accurate, harder to predict. All right, so here are some examples of these things. Starting with the picture on the left here, this is one of our attachments from Nature's Fury 2013. This was designed to lift our robot over top of some obstacles. It was intended that you were supposed to drive over it, but we found a loophole in this where we could latch onto the wall and just lift our robot and drive kind of off the wall over top of them, and it would still count. So because we were lifting our entire robot, we had to be really strong. That's why this is one of our examples for cross spacing. Now it is fairly old, so there's a few pieces missing, as you can probably tell. But you can see cross spacing, basically what it is something that supports something else in a different direction. So as you can see there are beams in the center, they're going in a different direction. These ones here, I'm not sure you can see my mouse, I think you can. Beams in a different direction than the uprights here. And that's just to make sure that it stays together, doesn't pull apart, and same with the ones on the bottom here. Makes it easier to stick together.
And not twist. So
not twist.
This is something that we really didn't want to move at all. So if you were to, move this with your hands to try and twist it up, it would stay pretty rigid.
Yeah. All right. To the right of that, this is an example of weight distribution. This is a trick we used to use a lot when we had really heavy attachments. Now, this is just an example, so it's not particularly heavy, but you'd use this on something that drags a lot to control where the points of contact are, to try and distribute the weight so that it drags evenly. That's what we use these quarter pegs for. You can also use half peg. There's the little blue things here, just to make sure that it doesn't drag.
And this is upside down right now, but you would flip this over, and then the only points of contact on the field mat would be the little blue pegs there.
Yeah. All right, so strong building. Continuing on with this, we have some more examples of cross bracing. This here is just a way of attaching something that's ejecting out of your robot in a strong way so that it won't twist. This piece won't twist at all if you were to push on it left or right from the L beam here. And then just to the right of that, this is one of our robots that we've made. And this is an example of a cantilevered axle. A lot of teams have nothing on the other side of their wheels. It's just attached to the motor, which means that it's cantilevered. Because it's cantilevered, the wheels over time will kind of start to flex out if your robot is heavy, and that means that your axles aren't straight and you're not going to be driving consistently because it's going to be kind of bouncing along as your axles bend over time. That's not good, and we decided to fix the problem by adding bracing on the outside that captures the other end of the axle, just like it is here.
So those are just a few examples of the different ways that you can apply those techniques to specific instances to make your robot stronger. But there's obviously many more ways to apply those same concepts that we talked about. So the next thing we're going to talk about is simplicity in design. And that's really important because a simple robot is usually easier to maintain. It can offer you more options and reduce the amount of Lego that you need so that you're not just limiting yourself to using motors or it just kind of gives you more options. Some of these things that we're going to be talking about are also often faster than motors, so it just gives you kind of an alternative that has some strengths over using motors for some situations. So one thing that we do is we like to use simple mechanisms that don't require motors, and that can be a simple machine, which is just a basic mechanical device that applies or directs force. So that could be a lever, wheel and axle, pulley, inclined plane, wedge, or screw. You probably learned about those in school. And another thing is that we often use is elastic powered mechanisms, which can be faster. That's one of the main things that are faster than motors in some cases. And this helps to free up your motors for things that you really need the motors for. And also allows you to do multiple missions or multiple actions and movements at the same time because you're not limited to the one motion of whatever motor you're using. We use these really frequently in our attachments when we were on the team, and we're going to show you some examples of what we did.
So this is just an example of what not to do. This is a swerve drive. Kind of hard to tell. Don't overcomplicate things unnecessarily. This is an example of doing that. You really don't need a swerve drive in FLL. Don't do it.
Logan just did it for fun, so. Okay, so the first example that we have here is from 2006, which is actually the year that before I joined the team, but it was the first year of our team existing. So this is a wedge, and on the side here we have just larger pictures of the mission model that we're interacting with, but it's just a really long axle with a magnet at the end, and it was really hard to detach it using a robot. So what our team did is we used a wedge that was activated by pneumatics. And I'll just play the video to show here. So we just drive forward and then it ejects over here. This pops up and then we leave that behind, which we'll talk about later as well. But a wedge can be really helpful for just, doing things in that one motion, or, just helping to redirect the force in the direction that you need it to go. Another example that we have that we've used a lot on our robots is a funnel. So this robot was from Smart Move, so 2009, 2010. And there was this mission model in the middle of the field that we had to drive over, and we kept hitting it whenever we were trying to drive over it. So what we did is we added these little, what we call J-beams, so that when it entered over the, so let's say the mission model that we're driving over is over here, these J-beams would help direct the robot so that it would drive over the mission model straight, by starting out with a big range to collect the mission model in, and then angling it into the width of the actual full mission model so that we always knew where we were and we wouldn't get caught on it and get stuck. So that's something that we used for that specific year, but we also used funnels a lot when we had a plow, just to have a really wide entry point, and then be able to collect it a little bit easier than if you just had straight beams. Another model that we used, I don't remember which year this was from, we used it multiple years, but this is a lever activated one, and I'll just play the video to show this. So I'm moving this with my finger, but this is actually something that we activated either by driving into a wall or by driving into a mission model. So it's just a little lever that you push, and then it empties the bucket onto or into whatever you need to do. So that's something that can be very easily done without using a motor, and it'll just be done by simply driving into something, which makes it really fast and really convenient and really simple. So you don't have to rely on your program to do that part as well. Another mechanism that we used a lot was a one-way valve, which is just a little, I'll play the video. It's easier to explain with the video. So basically this little drop down thing here can go one way, but not the other way. So we use this, like in this example, we used it to pick up a loop. This is something that we did a lot. We don't always use the same materials. We've made this out of axles many times and it worked really well. We've also used one-way valves for plows. So just having basically that same exact concept, but having the whole thing wider across the front of a plow so that when you pick something up, you don't have to worry about turning around and driving back to base in a certain direction in order to keep all the stuff in your plow. So you could just drive forward and then come back immediately and still keep all of the things that you picked up with the use of the one-way valve. The next example we have here is another one-way valve, but we also have an inclined plane here. So this looks kind of ridiculous, but it is pretty simple. It's just we attached it all to one thing, so it looks like a monstrosity. So this was from Body Forward. Logan's in the back here. This is me with my wonderful pigtails. And I'll show you what happens in this mission here. Okay, so this little claw thing that we have over here goes over top of the bone so that when we drive back, we're able to pull it back without having an extra motion or anything. It just does it by itself. So I'll play it again and point out that one thing again. So it goes over top. It can slide over easily, but then when you come back, it doesn't allow to move in that direction. So it pulls the bone back with it. And that's something that really helped us. We use this constantly when we were building our robots. The other machine we have here is this ramp for our car. We call this little car Bumblebee. And we just used that because this was the race kind of mission, shared mission. So there was a hand on the other side of the table and you had to do this really quick to get the patent first. So we wanted to do that really fast. So instead of driving across the entire field, we decided we'd send a little guy out there to do it for us. So we just sent it down a ramp so that it would build up the momentum and speed that it needed in order to get there. and that worked really well for us. So it looks pretty complicated, but those two things, it's really just all those simple things combined together that makes it look like it's a little bit bigger or more complicated, but they're really quite simple. Ooh. There we go. Logan, do you want to talk about this example here?
So this is another one from Body Forward. This is one that I built. This is basically a ratchet, really kind of simplified ratchet where we use elastics on these. I'm not sure exactly what they're called, but they're like kind of gears. These yellow things
like
right
the
here.
knob
gears.
Yeah.
Is what we call them. There's a little beam here, which is elasticized. And it's a ratchet, which means that it can only go one way. It can only go down in this case. And if you try to push it the other way, the beam would stop it, and it wouldn't be able to go that direction. So the way we used it is we had to pick up, I think it was a scientist, right?
It was a doctor, I
Oh,
think.
doctor. We used the wall to activate it, to push it down, initially get it over the force it needs to overcome the elastic. So I'll just show it again. It's the wall, comes down, and because it's a ratchet, it locks there and then keeps it there. So that when we bring it back, the doctor comes back with it, and then it comes at the bottom just for easy access.
So this is a really simple thing that didn't require a motor because we're using elastics. And then here's another application, once again for Smart Move. This is the mission model that I was talking about before that we had to drive over. This is what we call this the chicken wing. And essentially this is just a little panel that we had on the side of our robot that sprung out with the use of elastics. So it's kind of hard to tell in this video, but there's elastics along the side here that act as a spring to deploy it. And then we have a little elastic here that was attached to a little beam that was motorized. So just to let go of the elastic to activate it. And then it only goes out a certain distance because we had a little string that's attached to the chicken wing. So this is just activating these mission models, which we had to knock. So it was really simple, but there was very little space that we had to work in it, and we didn't want to, drive forward and bump one, drive forward and bump the other. So we just decided to do it as we drove past, and elastics worked really well to do that simply and effectively. So that was one of my favorite things that I worked on. And it'll play in these videos again. Okay, so the next part of simplicity in design is having multi-purpose attachments. So we always looked for ways to adapt attachments so that they would work well for multiple missions. And I don't mean just, like using necessarily the same thing to do multiple missions. It's really looking to make sure that it is the best that it can be for both of those things and combining them into one thing. So that could be having a plow with certain things on it that help with multiple missions, or just attaching multiple things together so that they work well for multiple things, and that will save you Lego because you have to build fewer attachments, and time because you don't have to swap attachments as frequently because you're using the same attachments. We always tried to allow for a margin of error whenever that was possible, so that things would work even if the robot was a little bit off, because things inevitably vary. Your table conditions, your robot conditions, your battery is low, things are not always consistent. You can't rely on them to be super consistent all of the time. So if you can make your attachments so that they allow for a little bit of error, it really helps to be able to complete those missions more reliably and effectively. So examples of that would be widening your plow, or having like the funnel like we were talking about before, or having, if you're picking up a loop, having multiple spokes to do that if you're so that if it's a little bit off, you don't miss that window and there's another one that can help pick it up. So those are just two examples of ways that you could do that, but it's really important and makes a big difference in your robot performance. Another important thing to do is to match the motion that your mechanism moves in to the motion that's required for a mission model. So if it's something that you push in, that's probably a great way to, use a linear motion or drive into it rather than lowering an arm like this and doing a rotational movement like that. There was a mission model in Senior Solutions that was a weight machine that kind of lifted on a rotational motion there. But that doesn't necessarily mean that you have to use a rotational motion. It just you wanted to pull it up. So just thinking about what motion works best to activate that model, and then trying to build your mechanism to match that wherever possible. Otherwise, you're going to be using your force inefficiently and applying it in directions that don't really help. So just it helps a lot to think about that while you're designing. And this isn't to say that simple is always better, but from our experience, most often it did end up being better. Sometimes a more complex solution works really well, and you just have to, kind of think about that and be really conscious of not overcomplicating things if it's not necessary. So always kind of check in and be like, does this make sense to do, or are we kind of taking this in a direction that doesn't need to go? And just evaluating that as you go.
Just to add one thing, oftentimes when people see our robots, they think, wow, that's really complicated. When in reality, it's really not. All of our attachments are basically just a whole bunch of simple machines put together. They're all just very simple things for all the different things we're doing in that mission, and then you just put them all in one attachment, making it look really big and complicated.
Mm-hmm. I think we also try to do, like we said earlier, trying to do multiple things at the same time, which is something that we're going to be talking about in our session tomorrow as well. But because there's so much attached to the robot at once, it looks a little bit like a monstrosity. People used to joke, like, does that actually fit in base? And it's like, yes, it does. It's very close, but it looks a lot scarier than it is. And then we just have a video here on the side to show what a 4-bar here is, which is just a specific type of motion. So this doesn't have anything attached to us, but it's something that we used on our robot in 2010 for 2010 for body forward. So this is what our primary motorized mechanism was, and it just it's an interesting motion because it makes it rotational, but it means that the end is always parallel with this bar here, so it's always going to be perpendicular to parallel with the ground if you have something sticking out off of it. So that can be really helpful for certain missions as well.
So modularity is another really important part of any robot. So modularity, what is it? It's the degree to which components can be separated and combined. So why is this important? It's very important for flexibility of attachments, to make it easier to maintain your robots, so that you're not ripping pegs and other pieces out of it and accidentally taking more than you wanted.
Or just having to dissect your robot to change your battery or change an attachment.
Yeah. You want to make sure that everything's easily accessible and makes sense the way it's put together to do that. Another one is quick and easy attachment changes. So this is something we prioritized really highly. We kind of developed a way of doing this. We'll show you later to make it as fast as possible, and we think we found a pretty good way to do that. So ways to make attachments modular. Generally avoid friction in your attachments. You don't want to be attaching something by using these normal methods for putting Lego together. You don't want to be putting pegs in the normal way, because if you do that, for one thing, if you're attaching attachments in the same place, you might accidentally leave a peg behind, and it will get in the way of other attachments. But also, it's not very fast. You have to line it up really accurately. So that kind of makes it difficult, not necessarily the best way to do that. Better ways to do it might be gravity. We often use gravity. We use magnets, more so in the past, because recent years we haven't been able to leave stuff on the field. Some more things are sliding axles through peg holes, or just normal holes, to make it
so to avoid the friction.
Avoid the friction. It's just sitting there. And to slide beams through slots and stuff like that. Sometimes it's helpful to detach part of your robot outside of home. So if you have a big chunk of your robot that's used to activate a specific mission model. And if the year allows it, some years you can't, you can leave it there, do that. Especially if it's near the beginning of the run, because you want to make your robot as small as possible, generally, so that you don't have to worry about as being as accurate as you don't have to worry about being as accurate not to hit other mission models or
Just allows you to be more maneuverable around the field.
Generally, it's a good thing to leave things behind unless it'll get in your way later. Yeah. Okay, so here's some examples. This is something we did for a long time. This is magnets. As you can see, it's very easy. This is why we did it. It's quick, automatic lineup, just attaches, and you're good to go. A little bit of a drawback: if you mess up your programming, you're going to lose it, and you're not going to be able to pick it up. So
it's easy to detach that on the field. Is
yes.
What you mean? Yeah.
It's a good way to detach on the field. We use a lot to do that. I don't remember if we did it in the body work video, but
yes, your attachment was attached using magnets on the front. Yeah.
Okay. Oh, where'd my mouse go? Okay, and the second one here, this is using axles. This is actually the axle peg connector. And you just sit it on the top of a beam just like that. It's easy attachment. You might want to fill the other holes if you're not using them for other attachments, just to make sure you're putting it in the right spot. It's also very easy and not much of a drawback to this unless you can somehow flip it up off of it. And then the last one here, this is what we kind of came up with over the years. And we think it's a pretty good design. We call it a skirt.
I turned on the audio.
There's audio for this one.
Surprise.
So basically what this is a it's a attachment that is standard for all of our runs. So each run will have one of these as its base, and then we'll have all kinds of things spreading from that. And then at the beginning of it, we'll put it on really quick and easy, just like that. It'll, in this case, it connects motors in case we needed power on our attachments. And then you can also detach it very easily. This one was a testing one, so you might be able to see that one of our attachment methods kind of broke off with it, but that's okay. That's just how it'll go. There we go.
Yeah, if I just can go back a slide for a second. That's okay. So this, I don't know if you said, but we call this the skirt.
Yes.
And it just fits over top without, and it's just attached using its own weight essentially. So you don't need to have any pegs or anything connecting there. It's really helpful to always attach your attachments, like Logan said, in the same place every single time. So one of the benefits of this type of modularity attachment method is that it's always the same. It's always in the same spot, so you don't have to think about which hole do I need to put this into, or oh, I forgot that this one attaches differently. It's just always the same, so it's really easy. Same thing with the magnets, because those just snap into place. This one here is great if you block off the adjacent holes. You can maybe mark them with a colored peg on either side just to like show where you need to put them so that you don't accidentally put them in the wrong spot. But this has made a really big difference in speeding things up and just making it easier overall.
Yep.
So the last thing that we're going to talk about is prototyping and iteration. So why is this important? For prototyping, it's really helpful to explore ideas before you fully commit to it. So this is what we call doing a proof of concept, just to show if something is actually has potential to work properly, or if it's something that is not worth putting any more time into. So just using a really basic scaled down version, or a something with less intensive bracing like Logan was talking about earlier, and just really bare bones trying to prove whether or not something will work, so that you make effective use of your time. This will also prototyping and iteration will also help improve your robot over time, to be more efficient, effective, strong, simplistic, all of the things that we've talked about earlier.
Mhm.
And it's really important to remember that you don't have to get it right the first time. It's totally okay to try something and not have it work, and then to work on that and improve it and iterate it so that it's more effective going forward. So don't be afraid to try to do those things. But we recommend, if you are going to make a prototype or iterate it and make a better version of it, always try to do a separate version. So don't take apart something if it's the best thing that you have, and always try to make like a separate version of it, so that you always have a fallback and you don't accidentally forget like how something was assembled or whatever, and then not have a way to figure that out.
We've done that before.
Yeah, learn from the hard way. So it's really important also to know when to leave it alone. If it works really well, or if you're really short on time, you might not want to risk making any more changes. So don't take apart your robot the night before competition to try and make it better. It's not worth it. You want to go with what you have and try to make that the best you can. So just make sure that you have the time and the ability to do that before you make any changes that are impossible to undo. So on the last slide that we have here, we just have a bunch of pictures of our robots over time, starting from our first year as a team in 2006 to the robot that we showed earlier. We have a few years missing in here because we didn't have enough space. But you can see that our robots have changed a lot. We've tried a lot of different things. We tried a forklift this year. It was good for some things, was not good for other things. That's why we didn't do it after that. This is our 4-bar robot here, which doesn't have part of it on in this picture. But that was something that we tried and we liked different parts of that. And then as you can see, we got progressively smaller and more square over time. And that, like Logan said, is for maneuverability. Man, that word is hard to say. So it's just really easy to get around the field, and really easy to line up on things, which is something that we're going to be talking about tomorrow as well, which being square really helps for. But we always have a lot of bracing. We've experimented with different motor orientations and different types and where our sensors are positioned and all that kind of stuff. And it's changed a lot. So don't be afraid to try different things. If it doesn't work out, that's okay. And just always try to keep improving your robots and your attachments. So with that, that is the end of our presentation. And if you have any questions, you're welcome to ask them now. And if we run out of time, you can always reach out to us at info@wafflesrobotics.com, and we can send you an email back to answer any questions or provide any support that you need.
All right.
There's a question in the chat. Somebody asked what type of elastics you guys use.
For first of all, you have to use Lego elastics. Any other elastic is illegal. Those are really expensive, so that's kind of unfortunate, but we use different ones for different situations. Oftentimes we use the larger ones, which I think are yellow, just because we like to have it span a larger distance rather than the smaller, like white or black ones, which aren't as useful in our eyes, but it's still, they all have a place. It just kind of depends on the situation. Like in this one here, we use a yellow one.
This one's blue here too.
Never mind blue.
And we have red ones on this robot here, but they're all Lego branded because that's the only type that you're allowed to use.
Yeah. So I hope that answers your question.
I believe there was also, Chris also asked a second question that said, where do you get the Lego magnets?
Lego magnets. It's been a long time.
Where did we order those from? I don't remember. They definitely came with some sets. I don't think they do anymore. But there are definitely, I think there was a specific site that is it Bricklink or something? I can't remember off the top of my head because it's been so long. But if you Google it, I'm sure that there'll be things that pop up on where to get those magnets from, which are also Lego branded because
Excuse me. Excuse me.
Yep.
I'm pretty sure the magnets come with a Star Destroyer set.
Started
Possibly.
from very possibly. I think we got ours from the first year of the team. As you saw the first mission there, that was attached using magnets, so we happened to bump into them on the first year there.
Yeah,
And
so we
just
knew
kind of-
we knew they existed from the start.
And that's why we came up with the idea to use them, I think. Yeah, so they definitely came in sets. I'm not sure exactly which ones. Could have been the Star Destroyer or any other one. I'm not sure.
Any other questions? Feel free to just unmute yourself or type them in the chat if there was anything you wanted to know from their presentation. A question came in the chat that said, how did you guys learn all these things? There are so many good tips.
A lot of years of experience. Like we said, we were both on the team for 5 years as a student. So we started when we were 8 and went through until we finished grade 9. So that in itself is a long time to try things, fail things, do things better, and just kind of see what other people are doing and try things ourselves. And then because we've been involved in our teams as mentors after graduating too, it definitely has extra years to help with that. It's all just trial and error, really.
Yeah, just a good way to make sure you remember all of it is often at times at the end of a season, at the beginning of a new season, we'll kind of look back on our past season and see what we really liked about it. So if there's some specific thing, if we discovered one-way valves that year, if we discovered, whatever mechanism we really liked or robot aspect we really liked, we would take those and try and keep them as much as possible. That's why we have these robots. Most teams don't keep their robots together, as far as I know. We keep them together so that we can remember what our mistakes were for those robots and kind of learn from them. We often keep together a lot of our attachments as well.
For inspiration, yeah.
Yes.
For future years. But yeah, that's a good point. We did do a review at the beginning and end of each season to make sure that we didn't lose any of the things that we had learned, because that's something that we really prioritized, because there's lots of things that we didn't do great. Like I said, the forklift, we used a worm gear, it was strong, it was very, very, very slow. So we did not do that again. There's probably other ways to do that's better, but with the method that we did, that wasn't great, and we just learned that from trying it, and made sure to review and collect all of those important lessons that we learned.
Awesome. We have time for about one other question. If anybody, looks like there's one in the chat that came. Which mission did you like the most?
Which mission?
Mission most.
Honestly, I think my favorite one was if this will let me change the slide. This one was my favorite. So this is one that I worked on myself. So I programmed it. Not that that's really anything special because it's just driving forward and backwards. But I worked on the attachments for this one, and I really liked the idea of this car. We actually used this the previous year too for another mission. And I don't know, I thought that was really fun, and it was really a little car, and to have all those things happen at once and have it really be effective. So that was really fun for me to work on.
Yeah, I think mine, we don't have it in this slide, but or in this slideshow, but it was probably World-Class, was it? The cloud mission? I think that was World-Class. It was our first mission of World-Class where we did a whole bunch of really cool things, and specifically the cloud mission I thought was, or maybe that was seniors, I don't remember.
It
One of those years.
mix them all together.
Too many years to remember. Anyways, the first one that I worked on there, I think that was probably my favorite. Very learned a lot on that mission. So
Nature's Fury, our first mission, was also really fun. It was kind of
True.
like this one where it's just we drive forward and then we have a bunch of things happen at once that
Yeah.
look really, complicated, but it's just little bits all put together. We don't have a good video of that, but there is a teaser video of it on our YouTube channel if you wanted to watch it. It's pretty cool, and just everything happens really fast and then drives back to base. So that one was also really fun.
it's like a 6-second mission. or
Yeah,
something.
it's really short.
Yeah.
So that brings us to the end of our session today. So I wanted to say thank you to Logan and Eden. You guys had such an informative presentation that had so much technical advice that I'm sure will be very helpful to all the teams here. And I really liked what you guys said about going with simple solutions and not trying to overcomplicate things, because simple is almost always the way to go, and it can still be so fun for everyone to design. So I'm going to end the recording now.